So this is going to be the fourth section of Chapter 7 for stats. This is going to be about, again, doing a confidence interval estimate for a population average or mean, but this time we're going to be looking at situations where we don't know sigma, which is, if you don't remember, the population deviation. So remember, the deviation is kind of a gauge of how well your average describes the data. So the higher deviation you have, the more diversity you have in your data set. So your numbers are really scattered about. Whereas if you have a lower deviation, your numbers are more consistent. So a lower deviation means that your average is a better descriptor about what's actually happening in the data. And then a higher deviation is an indication that your average is not as good as a descriptor as you might want. Basically, think about it like this. If you have a higher deviation, let's say you're technically ages of people on a bus, and let's say you have an average of 18 and a deviation of 2. That means that if you have a deviation of 2 versus a deviation of, say, 20, that means that your guess, when someone asks you how old is somebody on this bus, if you guess 18, which is the average, if your deviation is 2, that means your guess is more likely to be closer to the correct answer of any person they pick than if your deviation was 20. Because if your deviation is 20 and you say, well, I guess that this person is 18 years old, well, that might be true because it's the average, but you have such a wide deviation that there's so much diversity in ages on the bus that you have a higher likelihood of being off the mark. So again, think of deviation as how varied your data set is. So let's estimate a population mean here. So remember, we did this in the last video, but we did know the standard deviation in the last one. We knew what sigma was. This time we don't know. Sorry, my mic got a little close there. This time we don't know what sigma is. We don't know the population deviation, which is usually how things go, right? If you're trying to estimate the population average, well, usually you need to know the average in order to get the deviation. So usually you don't know the deviation going into these. So because of this, we actually have to use something other than a z-score. We're going to use something called a student t-distribution. It's named after somebody who kind of invented it, quote unquote, under the pseudonym of student because he didn't want people to know who he was. There's a whole history behind it if you want to read that on your own time. But basically what this is basically a replacement for our z-scores. It's a way to standardize the scores, but because we don't know the population deviation, these t-distribution values account for greater variability in our answers. Basically, these values here, the t-scores, instead of the z-scores, the t-scores give us a wider berth or a wider guess range because we don't know the population deviation like we do for z-scores. So the requirements for using this is the same as the z-score and the same as the last video. You have to have a normally distribution population or sample size of bigger than 30, yada, yada, yada. So all the same things apply. Simple random sample. Again, we talked about these in the very first videos when we did population mean and population proportion. So the requirements for this haven't changed. So the sample mean, x bar, is still our point estimator. So remember, this is going to be kind of where we start our guesses. So if our average is 18 years old, then that's where we're going to start our guess, and then we're going to construct an interval based off that, centered around that. So the sample mean is still our, or the sample average is still our starting point for our estimator. So how do we get the standard or the t-scores here? And it's very similar to the z-score formula. The t-score formula is simply the average minus the deviation divided by, in this case, instead of doing sigma, it's S. So remember, S is the sample deviation rather than the population deviation. So S is the deviation you get from the sample of people you pick. So just to, again, kind of illustrate that a little bit, if I have a population of everybody in the US, so here is the entire population of the United States, I'm going to take a small sample of them, say about, well, I don't know, 100,000. So I take 100,000 of them, I run my data, and the standard deviation I get from this 100,000, that is my S. The standard deviation I get from everybody in the United States, that would be my sigma. Now again, we're dealing with situations in this video where I don't know what this is, therefore I use my sample deviation as a replacement, and I use t-scores instead of z-scores to account for the fact that I might have a greater variability than I know. Now to get the t-scores, you actually use another table of values, and you read it very similarly, but there's one new factor involved that z-scores don't have, and that's what the degrees of freedom are. So degrees of freedom, often abbreviated as n-1, is simply one less than the number of people in your sample. So if you have 50 people in your sample, your degrees of freedom, often called DF, your degrees of freedom is 49. Okay? That's all it is. The reason this is because it has to deal with the fact that if you're averaging something, which again we're estimating an average, if you're averaging something and you don't know what it is, the first n-1 values can be anything you want. The last value is kind of the one that determines the average. I'm not necessarily going to go into this because it's not as necessary to understand how to actually use the table, and this will probably be a video of its own here to get into this concept. But just this is not something we just throw in there randomly. There is a reason behind it. If you want to investigate that more on your own time, feel free. But it's going to be an entire new video if I wanted to get into why this n-1 thing here exists. To show you what the t-score table looks like, this is what it is. So we have our degrees of freedom on the side. So this is our n-1 column. So if you have a sample of 11 people, your degrees of freedom would be 10. So you'd be looking in this 10 row here, or this 10 row here. Now, the top part is where people get confused about the area in one tail versus area in two tails. We're going to be dealing with area in two tails for now. We don't necessarily have to worry about the area in one tail right now. That we'll get into that later. But this is basically your alpha. So think of these numbers right here as your alpha value. So remember, your confidence level is the percent that you feel that you're going to be correct. So if you construct a 95% confidence level, you're 95% sure that you're correct in a sense. That's kind of a layman's way of describing it. Which means that your alpha is the percent that you're incorrect. So if you want to construct a 95% confidence level, that means your alpha is going to be 0.05. So you'd be looking in this column right here, this 0.05 column. And again, we're going to deal with the area in two tails for now. So if you have a degrees of freedom, let's say you have 11 people in your sample and you want a 95% confidence level. Well, 11 people in your sample means look at the 10 degrees of freedom. A 95% confidence level means you want a 5% chance of being wrong. So that means that your t-score would be 2.228. So that's how you find this here. Your alpha is the top column. Your n-1 is the side column. You find out where they meet to get your t-score in the middle. Now you can also have negative t-scores. They're just the same thing, just on the negative side. So if you're doing a left tail test, you just change these to negative. But we didn't get into left or right tails yet, so don't worry about the left or right tail business over here. That's something for a later video. Just always use two tails for now. Don't worry about it. So let's go ahead and do an example here. So let's say we have a sample size of 23, and we want to find a 95% confidence level for our interval. Okay, so sample size is 23. We're going to assume that we have a normally distributed population because if you don't remember, one of the requirements is that this only works for normal distributions or if you have more than 30 people in your sample. So since we have less than 30 people, we say that it's normal because we needed that information there. So that requirement is checked off. So if I want my t-score here, what I would do is say, okay, I have 23 people. I'm going to subtract that from 1, and I'm going to get, whoa, that's not what I wanted to do. What the heck? Try this again here. I have 23 people minus 1, and that's going to give me 22. So my degrees of freedom is going to be 22 degrees of freedom because that is 1 less than the number of people in my sample. Not in my population, but in the people that I'm sampling. 22 is 1 less than the number I have. So I'm going to use 22. My alpha, if there's a 95% confidence level, that means my alpha is going to be 0.05. So remember, alpha is the chance that you're wrong. Confidence level is the chance that you're right. So 95% chance that I'm right, 5% chance that I'm wrong. So I'm going to look for 22 degrees of freedom with a alpha of 0.05. So 22 degrees of freedom, which is right here. Alpha of 0.05, which is right in the middle. So I'm going to find out where these cross, and I'm going to get a t-score of 2.074. So that is going to be my t-score or my critical value, 2.074. Remember, z-score, t-score, critical value all kind of mean the same thing. Critical value is the highest and lowest. Usually it was the highest. Why is that not erasing? That's weird. Okay. Usually our critical value is the highest and lowest z-score that we can use. That's odd. But in this case, it's just the highest and lowest t-score because we're using t-scores instead of z-scores. So this is the highest and lowest score I'm willing to accept to be within my 95% confidence range. So now we use this to get, what the heck? Now we use this to get the margin of error. All right, let me do something here real quick because this is just annoying now. Let me close this out and let me start this again. All right, I'm not sure why it stuck there, but okay. So let me go back to where we were here. Sorry about this, folks. All right, yep. N minus 1. Got our t-score in degrees of freedom. There we go. All right. So how do we find our margin of error? So the way we get our margin of error is the same way we did last time. We take our critical value times, again, in this case, instead of having sigma, we're going to have s because we don't know what the sigma is. We don't know what the standard deviation is for the entire population. So we use s instead for the sample deviation, divided by root n. And then our confidence interval is still point estimate minus margin of error, point estimate plus margin of error. Okay? So really the only difference from here on out is that we use the t-score in place of when we use the z-score. The calculation itself hasn't changed. So this is just a list of steps here in case you want to review those. Again, I'm not going to spend too much time on it because it's very similar to the last one, except we just use t-score instead. So let's go ahead and do an example here. So same idea here. We have 95% confidence level. We have 23 employees that we're sampling. The average age is said to be 47 years. The standard deviation is 7.2. We want to figure out if there's age discrimination among employment. So we're going to figure out what is our best guess for the average age of an employee in this situation. We want a 95% confidence level in our guess. We know that there are 23 employees that we're going to take as a sample. So there's not 23 employees total, just 23 employees that we're going to take as a sample. We have an average age of 47 years, and we have a deviation of 7.2 for the sample. So of these 23 employees, their average age is 47, and the deviation of these 23 employees' average age, kind of a weird thing to say, is 7.2. So think 47, give or take 7.2 years, which is a pretty high deviation. So um, thus, since we have 23 employees, we're going to use the same t-score as before, which is, again, degrees of freedom is 22. 95% confident means we have a 20.074 t-score. So again, we just use the table here. 22 degrees of freedom. 95% confident means a 5% alpha. So up top there, find out where they cross, and we get 2.074. So same t-score as before. Let's go ahead and do it in our margin of error business here. Come on. So our e-value is going to be our critical value, our t-score. Again, critical value, t-score, same thing. Critical value is just the highest and lowest t-score you're willing to accept. And again, this is plus or minus. Remember, these are always plus or minus. We just don't write the plus or minus because we do that at the end when we do the addition and subtraction down here. Our sample deviation was said to be 7.2 of the 23 employees. And again, we took a sample of 23 employees. So we calculate this all out here, and we get about 3.11. If you want to do that in the calculator, you can. So this is our margin of error. So one way we could write our age range here is we could say that it was 47 as the average age plus or minus 3.11 years. That would be one way to write the result of your confidence interval. Now, if you actually want an interval, which is actually the upper and lower bounds, you would write it in this way. Again, this is where the plus or minus comes in. So there is really a plus or minus in front of this t-score, but we just do it down here instead. So we take our average age minus 3.11 less than our guess, which is less than our average age, plus 3.11. So again, think of this mu here as simply a stand-in variable for the average. This is just kind of what we're guessing. I really do hate when it does that. There we go. So we're going to subtract and add here. We end up getting, if I do some rough math in my head here, about 43.9 less than mu less than, that'd be 50.11. So this would be my confidence interval, that the average age of an employee is somewhere between 43.9 and 50.11, which, again, if we round up here, we said that the average age of an employee is somewhere between 44 and 50, which is a pretty wide range. I wouldn't necessarily consider that age discrimination, but it depends on how narrowly you define age discrimination. And again, this is stuff that not only statisticians do, but lawyers and people in business and stuff do to figure out whether they're on track or whether they need to adjust something, whether they need to adjust their hiring practices, or if you're doing it with money and stuff like that, whether they need to adjust their business practices, or if something nefarious is going on, that sort of thing. But again, should be very similar to the last video, except we're using a t-score instead of a z-score. So the only thing you need to get used to is reading that t-score table, which actually, in my opinion, is a lot easier than the z-score table. But just get used to reading that t-score table, and everything else from there on out is the exact same. So the thing that people trip up on here from here on out is whether to use the t or the z, because remember, both of these, t and z-score, are used to figure out the population average. These are both trying to figure out the population average. The only difference in when you use them is whether you know your standard deviation for the population. So if you do know the standard deviation for the population, that is when you use a z-score test. If you don't know the standard deviation for the population, that is when you use a t-score test. Both of them require you to have an n bigger than 30 or a normal distribution. So again, this is just a requirement for both. The only difference between z or t is whether you know this value or not. So to give you an idea about what that might look like in a word problem, the first one here, it says that we surveyed 100,000 households and found that the average number of trees in the front and backyards for each of those households was about 3.5. So again, now obviously a house can't have zero point 0.5 of a tree, but out of the 100,000, we averaged all the number of trees that they had in both front and backyards, and we found it to come out to be about 3.5. From the data, we also found that the sample deviation is 1.25. So of these 100,000 households, the deviation of the number of trees is about 1.25. So using a 95% confidence level, find the average number of trees in the front and backyards of houses in the US. Well, in this case, this would be a case where we use the t-score. Why are we using a t-score instead of a z-score? Well, because we know the sample deviation, not the population deviation. We don't know what the deviation for the number of trees are for households in the entire US. All we know is the deviation for these 100 households in the entire US. So because our deviation applies to just my sample, I'm using a t-score. Okay? So I would look up in my t-score table, I'd have, let's see, if I surveyed 100,000, I'd have 99,999 as my degrees of freedom, which obviously doesn't have on this table here. So you would go to the largest one you have, which would just be large in this case. So if you're off the chart here, you just go to large. Similarly, if you have like a degrees of freedom of say 68, and there is no 68 on here, sorry about that. If you have a degrees of freedom of 68 and there are no 68s on here, you just go to the closest one, which in this case would be 70. So you can round your degrees of freedom as needed if you're using this table, if your table doesn't have one for you. But again, you would use a t-score in this case because your sample deviation applies to your sample, not the entire population. Whereas in number 2, same exact wording almost, but if you look here, still 100,000 households, same average, same deviation. But if you look here, it says, it is known from past analysis that the deviation for the number of trees in the front and backyards of houses in the US is 1.25. So this is saying that the deviation is applying to the houses in the United States. This is applying to every house all over the United States, not just my sample of 100,000. So this would be a case where I'm using the z-score because this 1.25 is applying to the entire population of houses in the United States, not just the 100,000 I took as a sample. Many times you're going to use a z-score. The way you know you're going to use a z-score is because it's telling you that the deviation is gotten from past data. So normally when people don't know the population deviation, they will go to past studies and past surveys. As long as they're recent enough, they will use that as their population deviation rather than just using a t-distribution. So if your word problem indicates something about, well, it's known from past data or given from previous studies that the deviation is this, that's probably indication that you're going to use a z-score. If they tell you the words sample deviation, or if they tell you the words the deviation of the sample, that is a red flag that you're going to be using a t-score. So if you have sample deviation, t-score. If your deviation applies just to the sample, t-score. If your deviation applies to the entire population because you got it from past data or for some reason it's known to you, that's when you use a z-score. Now, everything else about this is the exact same. So once again, if I give you a confidence interval, let's say the average number of pets people own, I'm 95% confident that's somewhere between 2 and 5. So this would be my confidence interval. If I want to get the sample average, I simply add these two together and divide by 2. So my sample average, my point estimator, would be 5 plus 2 over 2, which would end up being 3.5. So that's the sample I got. That's the average I got from my sample, and the margin of error is just them subtracted. So this is exactly the same thing we did in the last video. Um, so that would be my margin of error, which would end up being 1.5. So another way you could write this is the number of pets people own is somewhere between 3.5 plus or minus 1.5. So this going backward stuff hasn't changed. So everything from here on out is the exact same as it was for a z-score, so I'm not necessarily going to go over all that. But if you look at the last video, if you want to go backwards to find out your missing pieces, use the same exact methods as you do because the t-score had no impact on going backwards here. So that's it for this video. Again, the main thing to understand here is the difference of when to use a t and when to use a z-score. So as long as you know how to read the t-score table, which again I've talked about a few times in this video, so you can go back and check if you need to. And as long as you know how to differ between a t-score test and a z-score test. And again, the main difference here, once more, t-score test, your deviation applies just to your sample. Z-score test, your deviation applies to the entire population. So make that check first before you decide on which one to use. And again, in both cases here, you're estimating the average. So that's it for this video. We have one more confidence interval things to go through, and that is estimating a deviation. So we'll do that in the next video. Hopefully this helped you out. Have a good day, night, or afternoon. Wrong button.